You know, solar panels seem so simple, don't they? They just sit up on a roof, making power. But what if I told you that a lot of them are secretly, well, underachieving? In this explainer, we're going to unlock that secret. We're diving into the hidden software brains that hunt for every single last drop of power from the sun.
I mean, you see solar panels everywhere, right? And you probably just assume they're all cranking out power 100%. But the truth is, most panels have this hidden potential, a secret power reserve that just often goes totally untapped.
So, here's the core of the problem, the big dilemma. A solar panel's power output? It isn't just one fixed number. Oh no, it's a constantly moving target. Just think about a normal day. The sun comes up, a few clouds roll by, the temperature goes up and down. Every single one of these things changes the exact point where that panel produces its absolute maximum power. So it's not a static number, it's this dynamic, always shifting curve of possibilities. And this quote right here, it really just nails the challenge. The MPP, that's the maximum power point, it is the absolute sweet spot for making power. But like it says, it's not fixed. It's in this constant dance with the environment, always on the move. So, to get the absolute most out of any solar panel, you have to be able to find and operate at this one specific point, the very peak of that power curve at any given second. That one point is the whole key to unlocking a panel's true potential. Okay, so if that peak is always moving around, how in the world do you stay on it? You can't just, set it and forget it. You need a hunter, a tracker. And that is where this really clever bit of technology comes into play. So let's meet our hero, Maximum Power Point Tracking, or MPPT for short. Think of it like a super fast digital hunter living inside your solar equipment. Its only job, all day, every day, is to seek out, track, and lock onto that elusive maximum power point, making sure not a single watt of potential energy gets wasted. So how did these digital hunters actually work, especially back in the early days? Well, they used some pretty straightforward, but, surprisingly effective strategies. Let's take a look at the first generation of these power-seeking algorithms. The most common approach is it's kind of beautiful in its simplicity. It's called hill climbing. I want you to imagine you're a hiker on a hill, but it is pitch black out. You can't see a thing. To find the peak, what would you do? You'd probably take a step, right? If you went up, you'd know you're headed in the right direction and you'd take another step. If you went down, whoops, you'd turn around and try the other way. The most popular classic algorithm called Perturb and Observe uses that exact same logic. It's right there in the name. As you see here, first it perturbs. It just nudges the system's voltage a tiny bit. Then it observes the power output. Did power go up? Great, keep nudging that way. Did it go down? Okay, turn back, nudge the other way. It's a simple, constant process of climbing towards that peak. And Perturb and Observe wasn't the only game in town. A whole family of these kinds of algorithms was developed, and each one uses a slightly different twist on that same hill climbing idea. You had stuff like incremental conductance, open circuit voltage methods, and a few others. But they all shared that same core principle. Take a little step, measure the result, and just keep hunting for that peak. But, and you knew there was a but coming, right? These classic methods are simple little hill climbers. They have a huge critical weakness. There's a villain in this story that can throw them completely off the trail. A simple shadow. I mean, think about the real world, right? Especially in a city or a suburb. It's not always perfect, beautiful sunshine. So what happens when a tree branch shades just one or two panels? Or a chimney casts a shadow that slowly moves across the roof all day? Well, this is where that simple approach starts to fall apart. And here is exactly why. Under perfect, sunny conditions, our power curve is just one simple hill with one easy-to-find peak. But the moment a shadow falls on part of the array, it totally changes the landscape. It creates a complex mountain range with all these little peaks and valleys, a bunch of false summits. And this is the heart of the problem. Our simple hill climber, it gets confused. It finds the very first peak it stumbles upon and thinks, great, I'm at the top. It gets stuck on this little local peak, completely blind to the fact that the real highest peak, the global maximum, is way over on another part of the curve. It's leaving a ton of power just sitting on the table. So this partial sheeting problem, it was a huge deal. To solve it, engineers and researchers needed to develop much, much smarter hunters. This led to a whole new generation of advanced algorithms, a lot of them inspired by artificial intelligence, and even by the natural world. And when you put them side by side, the leap in performance is it's huge. Yeah, in perfect, uniform sunshine, the old methods are okay. But the absolute game changer is that efficiency in the shade. These advanced methods, they don't get trapped. They are designed to scan that entire landscape and find the one true global peak, no matter what. And you gotta love the names of these new hunters. Seriously, we've got algorithms like particle swarm optimization, which basically mimics a flock of birds all searching for food at the same time, or gray wolf optimization, which copies the pack hunting behavior of wolves. So instead of one blind hiker taking one step at a time, these AI-powered methods are like a coordinated search party. They spread out, they map the whole mountain range at once, and they make sure they always find the true highest peak. Okay, so we've talked about hikers and wolves and all these pretty complex algorithms. But so what? Why does any of this actually matter in the real world? Well, the answer is pretty simple. It means more clean energy from the exact same hardware. Look, this is not just some theoretical gain you'd see on a spreadsheet. Every single percentage point of efficiency that these smart algorithms can find means more real power harvested from the exact same solar panel. And this is so important in places like cities, where shadows from buildings and trees are just a constant fact of life. It makes solar power way more practical and productive right where most of us live. And you know what? The innovation isn't stopping. Just like this quote says, developers are now creating hybrid methods. They're combining the speed of the old school algorithms with the intelligence of the new advanced ones. They're trying to get the absolute best of both worlds, pushing the boundaries of what's possible even further. Which really, it leaves us with a pretty fascinating thought. We've just seen how pure software, just better code, can unlock a ton of hidden power in hardware that's already out there. So it kind of makes you wonder, right? If the solution to getting more energy isn't always building more stuff, but just writing smarter code, where else in our energy system is there massive potential, just hiding in plain sight, waiting for a better algorithm to come along and unlock